So our next presenters are all from Bayer and presenting on MOCCA via ADF data access. The first presenter is Henning Kaiser. He is the head of the digital transformation group for small molecule technologies at Bayer Crop Science. And the second presenter is Christian Haas, who during his PhD focused on analytical chemistry and then did a postdoc joint between MIT and his work at Bayer, and that's what he's going to speak about today. From here, he's currently moved on and is working at Agilent. And then our final speaker for this talk will be Laura DeRocco, who is at Bayer as well and is a lead knowledge engineer in the CMC department. So why don't we go ahead and take it away, Henning?
Yeah, thanks, Corey, for the kind introduction and opportunity to present a bit. So unlike the picture presents, MOCCA is not about Turkish coffee today, but I'm very proud that we can share, an multivariate online contextual chromatographic analysis, and we are going to explain what this means to you. That is actually an ADF use case that's enabled by the access of raw data. And I just need to get control of the slides. Thank you. So looking a bit back, I'd like to put this a bit into context. And I still remember when we still had face-to-face Allotrope Connect meetings. There was a lot of side discussions around what are the actual needs from Allotrope and when can we get to end-to-end use cases. And I put some anonymized quotes on the slide to show you why we actually ended up being in this chicken and egg dilemma. So what do we need first? Can you think about end-to-end use cases before we actually have enough raw data and context and all the models ready, or can we invert that? And to what extent do we need solution providers and to build Allotrope technology into commercial solutions that we on the end user case can actually use that? And today, I think we want to show you some ideas how we can overcome this chicken and egg dilemma. But the other way, I'm going to share something what was never publicly shared is, and this is from a Bayer internal workshop from 2017, what is part of the vision that we had back at that time for Allotrope. And I'd like to do a check-in on the mission goals so far. So I think we achieved something like ADF-based plug-and-play integration is something that we have already. So we see into major data platforms, we can ingest data from ADF-based. We see for the major, like 80% of the data that we generate in analytical labs, so chromatography data, mass spec data, there are commercial solutions available for all the major systems that we have. So Chromeleon, ChemStation, Empower, and for mass spec, Sykes, Analyst, and Excalibur. So right off the shelf, you can just use that, generate ADF data wherever it is. But looking down at where are actually the value cases, so things that you couldn't do without Allotrope, right? So that really are enabled and not just focusing on making data fair. So we've seen also presentations today, but really unlock untapped potential and make this use case. So we've focused a lot on the ingest part. So far in the last years, this is something we want to address and show you today as well. And the other thing is like what are hurdles? So what is in our way? Are we fully open source, or how can we make it easy, give easy access, and actually also make ADF scalable beyond the use in the classical like C# and Java environments that it was designed for? And so this is what we actually did. So we want to show you today a use case that actually paves the way for new ways of working in process chemistry. And I think it's the first of its kind closed loop reaction optimization use case that we have that actually leverage raw data, so real raw data for in-process decision making. And I think the new things are that you are not using analytical chemistry at somehow an off at-line decision making at the end of your experiment, but bringing the analytical labs out of the cellar right at the decision table, and having in-process decisions right there. And this is all published open source. You see the preprints published already, and Christian will share the GitLab repository as well. It's unlocking the data from its hostage. So we see the hostage of proprietary CDS systems and others, and it helps us to unhide and trace impurities down the way. And with that, I hope you're very eager to see the technical details and the actual story, and hand it over to Christian, who will share this with you.
Thanks a lot, Henning, and hello everyone also from my side. So yeah, as Henning already said, we really wanted to use ADF files or raw data in general, chromatographic raw data, to make in-process decisions fully automatically. And the first thing we thought about is that we want to move the whole part after the HPLC system itself in an open environment to be able in the end to go back from our decision and see why the decision happened as it did. So the goal was to have completely open actionable analytics, which means that we have database decisions overcoming proprietary data formats, and especially, and this is the part I will focus a little bit here, is overcoming proprietary data analysis algorithms, which we find usually in CDSs. So what we did is we developed a Python package for chromatographic data analysis. And instead of just using the classical chromatogram, where we look at the absorbance at one wavelength over the time, we decided to go for the full raw data absorbance array, which means we look at each time point, we look at every wavelength of our spectrum to get just more information out of it. And the first thing we did is we reproduced a lot of features which we also find in the CDS. So we have some peak picking, some peak integration, peak purity checks, and so on and so on. And then on the next step, we wanted to go one step further and have used this additional information we get from the spectral dimension to have peak assignments, compound tracking. So we built compound libraries, calibration libraries. And so this enabled us to find peaks, quantify them fully automatically. And last but not least, also the user has to somehow interact with this tool MOCCA. So what we have is we gave the user some control over the data analysis, but also we give back the user some interactive reporting to understand how the data analysis in the end worked. I would like to focus a little bit today on one of the features we implemented here, which would not have been possible without the use of the full raw data array, which is also provided by the ADF files. And this is the deconvolution of impure peaks. So why at all do we need that? In collaboration with our partners at colleagues at MIT, we set up a closed loop reaction optimization cycle, which should be an autonomous machine which optimizes our reaction conditions. I will just briefly go through what is happening here. So we have a Bayesian optimization algorithm, which is suggesting some experiments. These experiments are translated to a machine-readable recipe, which is then, the experiment is then performed by an automated reaction platform in the lab. Then out of this reaction, we take a sample, automatically transfer it to an HPLC system. Here, in the end, we export automatically raw data out of the HPLC system. Then MOCCA comes in and analyzes the data. And then from this analyzed data, from the peak table, so to speak, we extract objective values and control values for the process, feed it back to our Bayesian optimizer, the Bayesian optimizer learns from the previous experiments, suggests new experiments until our process is optimized. So in order to keep this cycle running, we obviously have to consider cases where unexpected impurities, side compounds out of the reaction start overlapping with our products, with our internal standards we use in the chromatography. So this is exactly why we decided there is definite need of peak deconvolution features, which enables us to keep this closed loop system running, although we have overlapping peaks in our chromatography. So I will not touch on the chemistry here. I think this is not super interesting for most of you. I just want to very briefly show you the results we got out here. So we optimized a certain chemical reaction over the reaction time and the temperature, but also we use different bases for the reaction, and we also use different solvents. And here on the upper plot, we have the yield plotted against the optimization round. So in the end, we had 12 rounds of optimization, and we plotted the yield. So this was our objective value, the yield of the reaction against the optimization round. And I just want to highlight as an example here our maximum point. So this was the optimized reaction conditions we found during the optimization, how the chromatogram looked. And the chromatogram here at 1.7 minutes, we see that this is our product peak. This is the 6 here. Started overlapping with an unexpected impurity, which is the alkylated base, which we added to the reaction. So every time we used this base, we had an overlapping peak with our product. And in this case now, MOCCA was able to resolve this issue by decomposing this overlapping peak into 2 components, 6 and 8, with the corresponding UV spectra. And so in this way, this raw data analysis really enabled us to use these closed loop settings and use HPLC as a reaction analysis tool in these closed loop settings. And with that, I just want to highlight that we really want to start here an open source community project if other people are interested. So we published the whole code source on GitHub. We also published a preprint with more use cases like that. So this is not the only use case we have done in our lab. So in case you are interested, feel free to read the corresponding paper, look in the GitHub, but also reach out if you have any questions. And we really think that with the allotrope framework, which we implemented in our package, we implemented an ADF parser, which parses ADF files for this raw data analysis. We really hope that we can enable an open source effort or push in the analytical chemistry community. And yeah, I think for the fair data principles, this should be clear for everyone here. So with that, I would hand over to Laura, who will explain how exactly we implemented the parser of ADF files in the Python environment.
Yes, many thanks. Now I'm taking the control, and once I can. Okay, there we are. So if Christian presented to you how to use completely the raw data from a chromatogram, now the other part we are missing in this story is how to access the metadata. So how to automatically extract the metadata we need to analyze that raw data. And the information that we needed from the metadata layer in allotrope is really specific, and we needed to extract a wavelength vector. So if it's true that we can extract the data cube, so absorbance and time with HA library, and it's quite trivial. It was less trivial finding the right wavelength vector. And how the wavelength vector is formatted in the data description layer is represented as a linear function. And so in our case, we needed to find out how to extract the two parameters 2 and 109 automatically from the layer. And so I would like to take you to the journey of the schemas of the data cube, of the ontology, and how we perform the query from the data set we needed to the parameters. And so we knew exactly that we were looking for the three-dimensional ultraviolet spectrum, and that was our data set. And we are aware that to find out the parameter, we need to find the function scale mapping. So following the path, we need to connect the data set to the mapping itself. And to the mapping, we need to navigate through the scale mapping and finding out the function scale mapping, so the parameters that we needed to extract. This is quite simple to follow the path. Is even simpler now with the use of H5LD and RDF libraries. So this is what simply we have done. We simply use H5DL to read the data description layer. From that, we customize and build up a specific query, a Sparkule query that extracts all the data set, and we were customizing our code for the three-dimensional ultraviolet spectrum. And then once you get the specific data set, then we follow the path and we extract the two parameters using mainly RDF lib because it's simpler. We choose the simpler solution. So, and what I would like you to grab from this function, from this slide, is that we have two very simple functions that were customized because we needed something customized for MOCCA. But as well as this is explicitly customized, this is also allows us to think more openly to go for a more generic solution and maybe having getting function that extract immediately for us the specific parameter when we need it, instead of customizing function for specific use cases. And with that, we are going to close our presentation, and I will hand it over to Henning for the closure remarks.
Yeah. Thank you, Laura, for showing that out. So I think what are the take-home messages? We've shown how you can actually read ADF data in Python without actually that there is an explicit ADF Python library. So in the combination of certain packages, so H5Py for the data cubes and the LD and the RDlib packages to extract the data description layer as well. So this is probably the first step for a native ADF Python library, and with that actually making ADF also more accessible for data science in general, and this is highly needed, I think, in particular in process and analytical chemistry as well. And with that, I think we are very proud also to share this very first or one of the first real raw data use cases using multidimensional raw data and creating business value and discovering something that was not able before without actually the use of ADF, and even more proud that we can publish this as open source and give this back to the community. And with that, we are very open for any questions. Have a look at the resources that Christian shared, so the GitHub repository in our publication. And thanks again for having us.
Great. Thank you to all of our speakers. That was a really interesting presentation.